so I'm going to start. So this is the last tutorial of this session, and probably Antonio will say something at the end, but we will maybe resume in the next during the first month of the next year. But for now, this is the last one of this session. So today I'm going to talk about memory efficient aggregations. And what does it mean? So this is something of one of those topics, or of those part of the code that have been added to the new to PyTorch Geometric version 2. Okay, and when we had the talk by Matthias in early summer this year, he introduced some of the things that I'm going to talk about. So those ideas were there, and these are tricks or methods to make everything more memory and computationally efficient. So my presentation has only two parts. So in the first one is just code. So I will switch to a Python notebook. And it's about some background on sparse matrices and the class SparseTensor. Okay, and then in the second part, I will come back to the slide and show how these can be used or are used within PyTorch Geometric. Okay, so for the first part, I switch to the tutorial, to the Python notebook now. So let me do that. Okay. So this is, as usual, can be downloaded. So it's not there yet, but it will be in the repository. And I'm going to talk about three things. So first, I will talk a bit about the representation of sparse matrices in general, so not in PyTorch Geometric in general, and then how this is implemented. So these ideas are used in the SparseTensor class. Maybe it's a bit too small. Should I? Okay. And finally, I will show you a couple of things about how this SparseTensor is used in the new version of PyTorch Geometric. And everything here is more or less or mainly taken from this link that you can follow here. So it's the corresponding page in the documentation that documents the use of SparseTensor and memory efficient operations. Okay, so the first part we are going to see how sparse matrices are represented in general. So if you want to have a very detailed introduction to the topic, you can have a look at this link in SciPy, so where different kind of sparse matrices are implemented, and then every advantage and disadvantage of every format is discussed. So what's the idea? So what is a sparse matrix? I mean, we all know that. So it's a matrix where a lot of entries are zeros. Okay, and in particular, these are of course very good to represent adjacency matrices of graphs. Okay, so so in the adjacency matrix, every entry represents the weight or of a link between the ith and jth node. And so in realistic graph, usually this matrix is almost always everywhere empty. Okay, so most of the edges of the possible edges are not there. Okay, and but just think about this for a moment about this as a general matrix. So it's a matrix with a lot of zeros, and we create it in this very efficient way. So you can just specify the index of the rows and the columns, and specify the data that you want to have in every one of these entries. So for example, in the row 2, column 2, we put the entry 1. So it's 2, 2, and we have a 1 here. Okay, and so on. And then a very inefficient way to initialize that is to initialize an empty matrix with 0 entries, and then just assign. Oh yeah, this is useless. I don't know why I added it here. It's from a previous version. So it's just initialize a 0 matrix, and then you can just fill in the data into the corresponding entries of the matrix. Okay. So this is not a sparse format. This is just a sparse matrix, but in SciPy and in general in scientific computing, there are different ways of representing sparse matrices. And one important thing to understand is that there are advantages and disadvantages of every format. So the first one is this COO format, which stands for coordinate format, so COO. And this format is very good for the construction of the matrix, and also is very convenient to transform a matrix, a sparse matrix, from this format to another one. So usually is the one that is used to construct a sparse matrix, and then you move it to the format where you want it to be. Okay, and this is exactly the format that we use above. So you just specify, you can construct a COO matrix by specifying exactly as before, a list of data and then a row and column index. And then you can also provide the shape, so the dimension the matrix. Okay, and this is represented in this sparse format. And then you can always go back to the dense format by this command to array. Sorry, it's a bit of noise. And
hey, I think there's a baby crying in the background. Maybe
I
that person to mute.
I can confirm. Yeah, I'm sorry. It's like that.
I can understand her. I mean, she don't likes sparse matrices.
No, she doesn't like math yet. Okay, but I mean, you can move back from the sparse format to there is this command to array or to dense, depending if you want a NumPy array or a SciPy matrix. But I mean, this goes back to a matrix with a lot of zeros filled. Okay, but it's quite clear that it's more convenient to use a sparse format because you just need to store these 6 numbers and plus the 6 values of the row index and the 6 values of the column index. Okay, so this is just plain and is what we used before, and then it's very easy to construct them by just you can specify a full matrix and you get a sparse one. Okay, so this is a basic format. Then there are other two. One is called CSR, which is compressed sparse row format, and the equivalent for the column is called compressed sparse column, CSC. Okay, and these are quite the opposite. So they are not so immediate to construct, but they are very good for operations. Okay, so the COO format is very good to construct the matrix, but it's not good to slice. So to do slicing operation, to select some matrices, and it's not good for arithmetic operation. But the other two formats are the opposite. So they are very good for entry-wise arithmetic operation. So if you want to sum or subtract two matrices, and the first one, and they are both good for matrix vector products. Okay, and then this CSR format is good for row slicing, but bad for column slicing. Okay, and that's the opposite for the CSC. Okay, so it's not perfect. So for matrix vector products, so the other one is better, but this is good for entry-wise arithmetic operation, and now is good for column slicing, but slow for row slicing. Okay, but both of them are quite expensive if you want to change the sparsity pattern. Okay, so the usual pipeline is construct a COO matrix where it's easy to insert values, and then move it to one of these ones, this CSR and CSC for arithmetic operation or matrix vector multiplication. So how does this work? So we start from the same matrix as before, just to visualize it. And now instead of providing a list of row and column indices and data, this works a bit differently. So first, this is the CSR format. So first you provide a list of indices, and these are the column indices, but they are now sorted according to the row. So you look at the first row. The first row has an entry only in the column 3, so you write a 3 here. So this is the same vector as col before, but it's just sorted in a different way. Okay. Then you look at the second row, and there are a non-zero entry in column 2, so you put a 2 here. Then the third one, it is non-zero in position 1 and 2, so 1, 2. Then the fourth row is empty, so nothing, and the fifth one is non-zero in 0 and 1. So you write it like that. Okay. So you just need to sort the row index. And then you provide the data with the same format. So this is just the corresponding value that you can find in the corresponding entry. And then there is a bit more tricky part, that is the index pointer. So instead of having a row index now, it just tells you what is the position of the column index in each row. Okay. So what does it mean? So we start from 0, then there is an entry for every row. Okay. And then you can look at so the first entry is 1, which tells you that if you look at the indices vector, so this one, where do I find the index corresponding to the first row? And this tells you that to go from position 0 to 1. Okay, so indeed 3 is the only index in the first row. Then the second one has only one entry, so it will be from 1 to 2. And then the third one is it has 2 entries, so it's from index 2 to index 4. Okay, so this should be a 4 here. All right. And then you write 4 here. Okay. Then in the fifth one, there is nothing, so the index are found in no position, so from 4 to 4. And then other two values here, so from 4 to 6. Okay, so this is not so there are automatic ways to generate these. It's not that relevant, but it's just to show you that there are different ways to represent the matrix, and depending on what you want to do. Okay, but anyhow, now you can construct a CSR matrix by passing these three vectors now. So the data, the indices, but now the pointers. But a matrix is just so it has a different representation. But if you go back to an NumPy array is again just the same matrix. Okay. And then the same thing can be done. I'm not going to do it here, but if you want to, you can have a look. It's the same thing for the CSC format. It's just that the role of the columns and the rows are exchanged. So, but then the construction is exactly the same. Okay, but now you got indices for the rows and pointers for the columns. But that's it. Okay, so essentially the message here is that sparse matrices are an efficient way to represent. So there are efficient data structures to represent sparse matrices, and depending on what you want to do with the matrix, you can use different formats. Okay. Now, how this helps in PyTorch Geometric. So there is a data type, a class SparseTensor. You can find the reference documentation here. So this is not the torch /sparse is a new package implemented by the same people from the team, so the same author of PyTorch Geometric, and I think is built around sparse torch sparse, but it provides some functionality that is designed to the use in PyTorch Geometric. Okay, so you need this library in particular, and the sparse tensor is just exactly the same thing as before. So it's a sparse matrix. Okay. And you can construct it as before. So as we said before, the efficient way to construct it is by passing, so via COO matrix, so pass row, column, and values, and it works exactly the same. With just the difference that instead of taking only a vector, it requires it to be a tensor of type torch long. So if you try to, so this works, okay, so you just get a sparse matrix, but if you try to pass only the list as before, it tells you that it doesn't work because you want. So there is an assertion that what is it? Yeah, I mean, this just needs to be of the format that but it's just an easy conversion, and then you have it. So it's just a sparse matrix as before. So you see what is the row, column, and value, what are the row, column, and value vector, and you also get some nice information about the size, the number of non-zero elements, so n and z, and then the density. So the 24% of the matrix is filled with numbers, and the rest is zeros. And there is this command as in the SciPy library to go back to a full matrix. Okay, so this is again just the same as before, but it can be constructed with this sparse tensor. Okay, and so a couple of details about this because it will be useful later. So one thing is that you can construct it sparse tensor by passing explicitly some values, and you get a matrix like this. But you can also omit them, and in that case, you just so the default value is just 1. Okay, so if you don't pass the value vector, you just get ones in the non-zero entries. Okay. And then there are a couple of useful operations to create and manipulate sparse tensor. So the first one is just you can pass a dense matrix, and will, as in the case of SciPy, it will take care of creating a sparse tensor. And also, and this may be a bit more handy, you can use a sparse matrix constructed as a COO SciPy matrix, and you get exactly the same. Okay, so I think this second use case may be nice because this is exactly so. On COO matrix is exactly the format that, so you can get this matrix from Network X, for example. So an adjacency matrix in the form of a sparse COO matrix. Okay, so this is a nice way to represent data type. Okay, and then so this is from SciPy or a full matrix to sparse tensor. There are also the opposite operations, so the inverse operation are implemented. So I'm going to show you. So there are this nice method COO, CSR, and CSC, and it gives back. They give back exactly the representation that we discussed before. So I'm going to show you the COO, and you get exactly the row, the column, and the value. But you can use the other two, and you got as we discussed before. So the column and the row pointer in the case of CSR, and row and column pointer in the other case. Okay, so it's very easy to go back and forth from the classical data representation and the one provided by the sparse tensor. So it's really nicely usable for if you have some data. And then there are plenty of, so I'm not going to execute all of these, but there are plenty of methods to manipulate sparse tensor, and all these methods behave exactly as you will expect for method defined for matrices. So in particular, there is a multiplication, so matrix vector multiplication, matrix multiplication, transpose, and slicing, and whatever, okay? And I think the format internally takes care of using the right format, for example, for slicing or for things like that. Okay, but now, so far it's only just linear algebra or not even linear algebra, so it's just a representation of matrices. And the point now is how this is useful within SciPy, within PyTorch Geometric, sorry. And the idea, of course, is that this is a useful format to represent adjacency matrices. Okay, so I show you what I mean. So we just load the usual data set. I already downloaded it, so that if you click this one, it's the usual command, so you get it from you download it. And if you visualize that, this is represented in the usual way. So it's node features, edge index, so in the form of a list of 2. So it's a source to target edge, and then one entry for each of the edges, and then plenty of other properties of the graph, okay? And in particular, we are interested in the edge index because we want to have a sparse representation of the matrix. And if you look at this is the usual thing. So there is a node, an edge between node 0 and 633, and so on, okay? And so from this one, it's very easy to construct a sparse tensor because you can just, so you just need to get the number of nodes, okay? And then you can just pass a list of row indices and column indices. And these are just the first and the second row of the edge index, okay? So you can explicitly construct a sparse tensor by from an edge index. So this is just a different way to represent exactly the same graph. Sorry, it's the same, only the connection pattern. So the features are not here. So it's just a sparse tensor with representing the edges. Okay, but it's really immediate to do that. But it's even more immediate because you can also do it in these ways. So instead of defining a data set and then doing an explicit conversion, you can do it directly. So there is a transform implemented in the transforms here. Okay, so so you can pass when you get your data set. So exactly as before, you can pass a transform like this, so to sparse tensor. And this does what we have done here automatically. So this just gives you the same data set, but now you see there is no edge index here, and you directly get the adjacency matrix, okay? Which is in the form of, is exactly what we had before. So it is of the correct size, like here, and you get the same number of non-zero entries, okay? And one thing to notice is that we are going to see this in a moment, but actually PyTorch Geometric stores the transpose of the adjacency matrix. I'm not sure why, but just remember, so this is quite nicely reported in the name. So by default, this is called, I mean, it has this T here, so it makes it clear that the matrix is transposed. Okay. And yeah, you can just get it and you see it is exactly what we had before when we created it by hand, okay? And then there are also utility method to do not utility method, but it's very easy to do the opposite. So the conversion also here. So if you start from a sparse tensor representation, like here, you can call this method. So you can first transpose the transpose adjacency matrix like here, and then call, for example, the COO method. This is one that we have seen before, and it gives you back row column index and the edge attributes, okay? And from that is very easy to construct back the edge index. So essentially, it's very easy to move from one format to the other one, and so this new class is perfectly integrated in all the rest of the library, okay? And so this is how it works, and now we are going to see why it matters. So the first use of this is that you can exactly exchange as you wish between the representation of a data set in terms of edge index or a data set in terms of transpose adjacency, okay? And for example, you can define a very easy, so I'm defining here a very easy convolutional layer, okay, which the input features are the features of our data and 4 output features. So this is just a random number. But it's nice because you can compute a convolution on, we pass the features of the dataset, and then you can pass the edge index, and it works. So this is, let's say, the classical way of doing that. But now, instead of the edge index, you can also pass an adjacency, so the adjacency matrix transpose. And as you can see, that's exactly the same thing. Okay, so essentially wherever or almost wherever. So there is a note in the library documentation that says that. So some part of the development is still under development. So, but essentially almost everywhere in the library where you can use one format, you can use also the other one without specifying anything. You just need to pass it. And so wherever you can pass an edge index, you can pass an adjacency matrix in sparse format, and everything will work nicely. Okay. Okay, but now so far is a bit. So it was only about representation. So it's a new representation of the same thing, and now. We go back to the presentation, and I want to comment on why all these matters for so how this is related to memory and computational efficiency. Okay, so in particular we move to the second part, and is the one about, so it will be very quick, is the one about the use of the sparse tensor within message passing. Okay. So just a quick recap. So how does message passing work? So we just define an example layer. So it's like this. So we have features, node features xi and j, and we want to compute transformed node features x prime I. So for the target nodes, and the usual thing is, as always, so you apply some nonlinearity to the initial features. So this is a general multi-layer perceptron here. And then there is an aggregation operation that in this case is the sum over the neighbors of the ith node. Okay, so this is the usual thing. And this is implemented in the library in a way that we have seen plenty of times. So, so from this, so there is in particular this message function that implements this part here. So the application of the multi-layer perceptron or whatever really on the input features, and then there is an aggregation function that is automatically called when you call the propagate method or the forward. The message is aggregated in a certain way. Okay, and if we look a bit more into what happens for this one, so this is again the same implementation of the simple convolution layer that does what was exactly the same thing that we had in the previous slide. So what's done here really is this two-step approach of gather and scatter. And the idea is that first there is so the source features are computed and the target features are computed for each the nodes. Okay, and then the message is computed as in the previous slide. So by applying MLP on the difference of the features. Okay, so really for every pair of nodes now, or for every edge, you compute. So you need to store twice this operation, this thing here. Okay, and now once this message is given, you can scatter, so-called the scatter operation. So this is the aggregation from. So this is essentially the operation that maps this MLP computed everywhere to whatever you need to transmit to the next layer according to the aggregation operation. Okay, so there is this idea of the two-step operation. And looking a bit more into these, so the first one, the gather operation, what it does is to collect all the features of the nodes and apply the message to it, or it's not applying the message, it's applying the nonlinearity in order to compute the message, so it's not formally correct. Okay, and in particular, it requires the explicit storage of the source and target features. Okay, like so this part here, and this in particular may require the storage of a lot of possible duplicated, especially if the graph is very dense. So if every node appears a lot of times in the edge index. Okay, and the second operation also has some limitation for large graph or for denser graph. So what it does is to aggregate the message according to the target node index. So there is this nice representation in the library. You just have a list of inputs or features, and then there is an index list that tells you where to look in the inputs to compute the output. Okay, so the color blue here corresponds to the index 0. So if you want to find the value for the index 0, you just can go and look at the inputs that have index 0, and then there is an aggregation operation, which is an addition in this case, and you get the output. Okay? But this is quite expensive. You need to go back and forth from all the entries. Okay. Okay, and in particular, both operations can be significantly simplified in terms of efficiency and storage by sparse matrix multiplication. And how is this done? So it's just it's very easy. So it's just replacing, let's say, pointwise operation with matrix vector multiplication. So there is an example in the library with this layer, the gene convolutional layer, which can be written like this. So if you write it in terms of message passing, it's just like this. So you take the sum of the features of the neighboring nodes, and then you add the features of the node itself multiplied by a certain coefficient, and then you apply the multi-layer perceptron to it. Okay, so this is the usual message passing definition of the method. But then if you vectorize this, so if you stack all the features in one matrix X prime, you see that immediately that the same thing can be written for all nodes at once in this format here. Okay, and now these are sparse matrices. So X is dense, but A is sparse because it's the TSSC matrix. Okay, and so the idea of this memory efficient aggregation is just to replace the left implementation with the right implementation, and the right implementation, uses the SparseTensor format for computing everything. Okay, and the idea is that this reduces a lot the memory requirement to store all the features computation, and also allows faster execution time because this matrix vector operation for sparse matrices are highly optimized, and you never compute something twice. Okay, and this is in general. So there is a note in the documentation that this is in general possible for most of the layers, and it is provided. So we'll show you in the next slide. So this step of using the approach on the right instead of one on the left is already implemented in the library, but it's not guaranteed by default that every possible layer that you can imagine can be transformed in an equivalent way on the right. But it's quite easy. So if you can write it in matrix vector product form, then you can do that. Okay, and then just to conclude, how is this implemented in the library? So the idea is that there is a new method that is called message and aggregate. And what it does is to just combine the method message and the method aggregate within one single call. Okay, so instead of calling them sequentially, you can, they are usually implicitly called sequentially. Now, there is a method that is called to perform both operations together. Okay, and the nice thing is that if you implement a layer and you write, so you define this method message and aggregate, and most of the method of the layers in the library have it implemented already, then it is automatically called. So whenever the library finds that this method is implemented, this one is called now in place of the other one. Okay. And so this is an example for the one that we have seen before, so the gene convolutional layer. So if you stop at the message is the old implementation, so it's exactly what we had before. Okay, so the message is that the feature, and then the aggregation is the one that we have seen in the previous slide in math format. But now there is a new method, message and aggregate, and what it does is to just do that simple operation that we have seen before. So it does implement the same thing in terms of a matrix vector multiplication plus a certain aggregation that you can pass to the method. Okay, and that's it really. So actually, this is completely transparent to the user. So if you provide if you pass to the forward method data in the form of a sparse tensor, and this method is implemented, that is called, and everything will be faster and less memory having. Okay.
Can I ask a quick question?
Yeah.
So if you go,
ahead.
Yeah. So if you look at the message and aggregate step, you're using like a matrix multiplication imported from Torch Sparse. So like if I just use a matrix multiplication in Torch, so that wouldn't work. So I have to use this special matrix multiplication from a Torch Spark. Is that the way it has to work?
I think in principle you can use whatever kind of multiplication you want. So I think this can be defined as you wish. But so this requires that you pass on a sparse. So these are the SNC transpose. I think is required to be a sparse tensor.
Right.
But then this is just a replacement for the matrix vector multiplication that is efficient for sparse matrices. If you use a plain torch multiplication, I think you lose the advantages of having.
I see. So like if I use plain torch multiplication, even if one of the matrix is represented by torch sparse tensor, you still wouldn't leverage all the advantage of a sparse matrix multiplication.
No, because I think this matmul is just so the one in torch sparse I think is just another writing of the same method. So I guess that sparse tensor is just a derived class from tensor, and it just re-implement this multiplication to work better with this format. So that is what I imagine to be the case. But but in principle, I think it's fine if you want to. So you don't get the advantages of using the sparse format, but in principle, I think you can write everything here. So it's just
right. I mean, like the main point of why we want to go use message and aggregate is to leverage that faster and efficiency, memory efficiency. Okay. And like I just going back to a few slides ago, so like I'm just thinking about, like if the message function takes both xi and xj, then you wouldn't be able to do this, right? So like so here you're saying
that's the point. So the thing is in the library is exactly written like that as soon as the layer doesn't require, I can check it out, but I mean there is a note exactly along those lines. So there is kind of a rule of thumb to understand if you can do that or not. Because it's not easy to
I see. Okay. I think like it will be very interesting to have some benchmark to see, on the both time side, using the sparse matrix and using the new function message / aggregate versus the traditional approach to see how much the time.
Yeah, exactly. I was going to ask these questions, like if Gabriele knows something about the real-time consumption in comparison between the tense message passing with this new one. I think it's. I mean, it's a simple question, but I think I will try it to see, just for curiosity. And to see also, the time.
And also, like I never done this, but like like from what you're saying, it does seem that there's a big impact on the memory, because before, you have to expand to xi plus like xj that many rows, like you have to have the xi xj combination there. So here you only have the x, so it's only at the node level rather than at the edge level. So I think like it would be nice to see some memory benchmark as well, but I never know how to do benchmark on the memory.
On the memory, that's true.
I'm also curious to reason about what happened if we are using GPU instead of CPU.
No, okay. These operations are completely. So that's something that I should have mentioned. Sorry, but this SparseTensor implements. So the nice thing is that it implements GPU efficient operation for sparse matrices. So it's already designed to be super fast on GPUs. So it's not about So that is already designed for that. One thing that I think may make a difference. So if you use the approach on the right, this one, you need to compute in a sense So I think you get a big advantage if you need to compute the feature representation for all nodes. So during training, that's surely an advantage. I don't know if you want to use the network for prediction. So if you want to compute just the representation of a few nodes because whatever kind of application, then the approach on the right forces you to compute it for. I mean, you can do sub-slicing of the metrics, but I don't know if it is. Probably will still be faster, I think. But I think you can see a smaller advantage over the left approach if you just need to have a few nodes.
Yeah, I totally agree with you. Yeah. Thank you, Gabriele, for the presentation.
Thank you for the questions.
And are there other questions, guys?
Okay.
Yeah, I don't have anything else.
Okay.